Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to diagonalize A. Diagonalize A. So I need an A. Let's do this. How about we're going to let A be the matrix? We'll derive. How about 0.5, 0.5, 0.6, 0.4. Well, we learned that if you diagonalize A by finding the if it has unique non-zero eigenvalues, then we also have independent eigenvectors, and then we can write A is x lambda x inverse. And the beauty of this then is that A raised to some power is the same as x lambda raised to that power x inverse. So today we're going to find that for this matrix A. We're going to find A and AK. Well, we do that. First thing we want to do is find the eigenvalues. So we want to solve the equation of lambda squared. Subtract the trace. That's going to be minus, the trace is 0.5 plus 0.4, so minus 0.9 lambda. Plus the determinant, and I have to write this out, that's 0.5 times 0.4, that's 0.02. Oh goodness. 0.02 minus 0.5 times 0.6 is that's 30, is 0.3. I think I did that wrong. 5 times 4 is 20, but 0.2. It should be 0.2. Okay, there we go. Gosh, sorry, I'm having a total brain fart there. Equals 0. All right, so I have lambda squared minus 0.9 lambda. 0.2 minus 0.3 is going to be minus 0.1 equals 0. Now, I'm not very good at finding, factoring that, so let's just use the quadratic formula. So I have that lambda is equal to 0.9 plus or minus the square root of 0.9 squared, so 0.81, minus 4 times 1 times the negative 0.1 over 2 times 1. Well, let's see, that's going to give me, so now I have lambda equals 0.9 plus or minus, that's going to be 0.81 plus 0.4. 0.81 plus 0.4. All of that is divided by 2. So we can say that lambda is equal to 0.9 plus or minus, this is going to be the square root of 1.21 over 2. Well, this is going to give me that lambda is equal to 0.9 plus or minus, the square root of 1.21 is 1.1 over 2. So lambda is 0.9 plus 1.1, that's 2 divided by 2 is 1. And then 0.9 minus 1.1 is minus 0.2 divided by 2 is going to be a minus 0.1, so minus 0.1. Those are my lambdas. Now I want to find my eigenvector. So let's do that. So my first eigenvector, we'll call it lambda 1, is 1. And so what we're going to solve is we're going to take the 0.5 minus 1, 0.6, 0.5, 0.4 minus 1. So remember what I'm solving here, I did that a little quick, is we're solving the equation of A minus lambda I, and in this case, the lambda is 1, or lambda 1I. So then this is going to give me the matrix, equals 0, so 0.4, 0.6, 0.5, 0.3. Oh, goodness. 0.5 minus 1, that's ridiculous. That's not 0.4, that's minus 0.5. And 0.4 minus, goodness gracious, I'm having an arithmetic mess of a day. 0.4 minus 1 is minus 0.6. Okay, there we go. And you can, this is going to equal 0, and we can do some row operations. And what we're going to find is we're going to find this problem of minus 0.5 x1 is equal to minus 0.6 x2. Well, this is going to be that x1 is 0.6 divided by 0.5 times x2. So x2 is free, so we can write our x1, our first eigenvector, is going to be 6/5 times, now we can just take any multiplier. So let's multiply it by 5. This becomes 6/5. There is the first eigenvector. Now we repeat. So lambda 1 equals minus 0.1, or lambda 2. So now I have 0.5 minus a negative 0.1. So it's really a plus 0.1, 0.6, 0.5. Then a 0.4 plus 0.1, 0.4 plus 0.1. Okay, and that's really the matrix of 0.6, 0.6, 0.5, 0.5 equals 0. And we could row reduce this, and what it's going to become is really we're just solving the problem of 1, 1, 0, 0. But the augment times some vector x2 equals 0. So this eigenvector here, this just says that we're going to have x1 is equal to minus 1x2. x2 is going to be free, so I'll write that, x2 is free. So x2, the eigenvector, is going to be minus 1, 1. That looks like the easiest choice. Okay, we've really done all the work now. Here we go. Our eigen x, our matrix of eigenvectors is 6, 5, minus 1, 1. And we can very simply find the x inverse. So x inverse, and you can always solve the augmented matrix, or you might remember the pattern that what happens is you switch the top left and the bottom right position, so 1, 6, and then you change the sign on the anti-diagonal. So this is going to be a 1 minus 5, and you multiply that by the reciprocal of the determinant. So this is 1 over 6 minus negative 5, which this is really going to be 11, so 1/11. So now we've got this. So now I can write this as, I'm going to go to another page. I'm going to take this, and let's write it this way. So let's write A here, and then we'll take it to the next page. So A is x, 6, 5, minus 1, 1. Now here's the interesting part. When you write lambda, when you write the matrix lambda, the order in which you write the eigenvectors has to match the order of the eigenvalues. So the eigenvector 6, 5 had an eigenvalue of 1. So 1 goes in that first spot. The eigenvector minus 1, 1 came from the eigenvalue of negative 0.1 times x inverse. This is 1 minus 5, 1, 6 times 1 over 11. Now I want to take, here we go, take that, copy it, and I'm going to turn this page off, go here, Okay, so that's A. Now, let's try something else. Let's find A to the K. A to the K. Well, we already just said that this is, all it affects is the lambda component. So this is just 6, 5, minus 1, 1. 1 raised to some power k, 0. 0 minus 0.1 raised to the power of k times 1 minus 5, 1, 6 times 1/11. Now, let's try this. Let's actually multiply out a to the k. So I'm going to work left to right. So this is going to be a 6 times, wait a minute, let's do one more thing. Because 1 to the k, well, we don't have to write it, but 1 to the k is just 1. So I'm going to have 6 times 1, which is going to be 6, minus 1 times 0, so that's just going to be a 6. And then again, row 1 times column 2, this is going to be a 0. And then we're going to have a minus 1 times negative 0.1 to the k. And then we're going to multiply again, row 2 times column 1. So this is going to be 5 times 1 plus 0, so this is going to be 5. And then we're going to have a 0, and then we're going to have another, this will be just be a 1 times minus 0.1 raised to the k times x inverse 1 minus 5, 1, 6, and 1/11. Okay, now let's multiply these out. So again, row 1, column 1, that's going to be a 6. So that's going to be a 6. And then it's going to be my plus 5 times minus 0.1 to the k. That's my first entry. Now my second entry, we're going to go row 1, column 2. That's going to be a 6. 6, and then we're going to have a minus 6 times negative 0.1 to the k. Okay, and then let's do this again. Row 2 times column 1, that's going to be a 5. So that's going to be a 5. And then we're going to have a minus 5 times negative 0.1 raised to the k. And then let's do this again. Now then row 2, column 2 is going to be 5 plus 6 times negative 0.1 raised to the k. All of that is multiplied by 1/11. Now this is where this problem gets interesting. What happens as k gets really, really large, as k goes to infinity? Well, a number between 0 and 1 raised to the infinity just becomes 0. So what we would say is a to the k, it becomes, or it approaches, well, all of these terms with negative 1s to the k's, they go away. And so we get this state. We have 6, 5, 6, 5. And that's it. That's what happens to a as k goes to infinity. And there it is. And that is an example of how you can diagonalize a matrix and how you can see the long-term effects of multiplication. In this particular example, because the columns of A add to 1, the A is called a Markov matrix. I hope that helps. Thanks for watching.